Welcome, students, to my video explanation of Lab 9, the final lab for our biochemistry one semester lab. This lab actually is optional if you've done all of the previous labs and are satisfied with the grade that you've gotten on them. But I'm still making this video so that you guys can do it if you guys want to or need to. So anyway, here goes. Let's go ahead and get into it. So as I outlined in our earlier lab, we're going to begin by opening up our software DS Viewer Pro, which for you, my students, should be available in our computer lab. We click here, and of course it brings up this weird window, and then we just click OK. Now what I'd like you to do is click Open and open up the file that I made available to you through Canvas, this 2HU 10,000 men. We'll go ahead and click on it and select Open. Now what we want to do is rotate around until we find our Tamiflu, and it's kind of embedded in here next to this +1. If you double click on it, we can see it right there. That is indeed the Tamiflu. We of course just want to focus on the Tamiflu itself as well as the active site that's immediately around it, because the stuff on the periphery doesn't really make any significant conformational changes. So having selected it, we'll go up here and select Edit, and then Select, and then we'll choose Group, Active Site 8A. We now hit Select and hit Close. It now lights up everything that's three-dimensionally within 8 angstroms of the selected molecule. We'll now go ahead and choose Copy, and then we'll open up a new document by clicking this icon. And now we choose Paste. We've now pasted our Tamiflu and the immediate perimeter of active site that's around it here onto this canvas. If we want to get a zoomed up picture, we can click this black box to maximize it here fit to screen. I'm not going to select Tamiflu itself by clicking on it right there and then going to View, Show Only. We'll go ahead and make it larger so that we can get a closer look at it. As you look at Tamiflu, you might remember me discussing in an earlier video that it has a very specific structure, and that this portion of it up here, the isopentyl group, was the one that was discovered to show the optimal activity for this molecule in vivo. As it turns out, some other researchers found another structural variant of Tamiflu that showed some interesting and useful properties as well. For that, we're going to go ahead and take a look at a peer-reviewed scientific publication. This publication was released through the Journal of the American Chemical Society, often just called JACS by chemists, by the groups of Shea and coworkers shown up here. The specific citation comes from 2007, volume 129, page 11,892. What we're going to do now is jump to page 2, where you see this scheme that shows a synthesis of some analogs of Tamiflu. I want to scroll down and look specifically at this analog number 3A. You'll notice that it has a nitrogen attached to an acetyl group right here. Now if you compare that to the original structure of Tamiflu, that is actually exactly the same. It also has this amine right here, which is also exactly the same as the original Tamiflu. The major difference, however, is that this group that they've labeled A is a phosphate group. That is a phosphorus that's doubly bonded to one oxygen and singly bonded to two separate OH groups. Now under physiological pH, those OH groups would be deprotonated, so they would be O- all in resonance with each other. So this analog 3A, as it turns out, showed of the various analogs that this group synthesized an increased comparative potency. And structurally, it's exactly the same as Tamiflu in all respects, with the exception of this one group that in Tamiflu is a carboxylate or CO2 group being replaced by a phosphate group. I want you to keep that in mind as we go back then to our Viewer Pro canvas. Okay, so here we are back at our Viewer Pro software. If you look closely at this structure and compare it with the structure that we were just examining in the paper, you'll notice once again that it is exactly the same in all respects, with one exception that I'll point out momentarily. For example, this group right here that's purple colored is a nitrogen, which under physiological pH is protonated, so it has 3 hydrogens on it. This purple group over here is also a nitrogen right here. It's single bonded to a carbon that's double bonded to an oxygen and then has a methyl group, a CH3 coming off of it. That is a nitrogen that is stuck to an acetyl group. This group over here is the one I was talking about. I've got a carbon that's double bonded to one oxygen, single bonded to another. Under physiological pH, the single bond of the oxygen is going to be deprotonated, so that these are in fact two oxygens that are in resonance with each other. This group is called a carboxylate group. Now what this research team did is they replaced the CO2- group with a phosphate group. And that's what we're going to do today. Then, following the same pattern that we did in our previous lab, we're going to calculate the new delta E of this new analog. So let's go ahead and do that. What we'll begin by doing is making sure that we've chosen our selection tool by clicking this arrow right here. We'll now choose the center of this bond and right-click it with your mouse. You now select Change Bond and choose Single. We'll now do the same thing to this bond right here. I want to have nice single bonds. These are single bonds to oxygens coming from this carbon. I now want to change this carbon to a phosphorus, so I click on it right there and type the letter P on my keyboard. It changes its color, and that is now phosphorus. I, of course, want this phosphorus to be doubly bonded to one oxygen and then singly bonded to the other two. Let's go ahead and select this section of the molecule, and now I'm going to copy it by using my keyboard and typing Control-C. If I now type Control-V, it pastes it. Now, you might not realize that it has been pasted, but if you click on it and drag it over here, indeed it has. Now, what I need to do now is create a bond between the phosphorus atom right here and the oxygen atom over here. So I'll go over here to my pencil tool and select it. What I do now is I point right at the phosphorus atom, click it, and then I drag it over here to this oxygen and click it. I've now formed a bond between my phosphorus and oxygen. I'm now going to go back to the select tool and choose this phosphorus right here and then delete it. I now have a phosphorus that's bonded to 3 oxygens. Now, as you looked at the previous paper, you'd notice that the phosphorus's bond to one of these oxygens was a double bond, and to the others was a single bond. That is, it was singly bonded to 2 OH groups. However, at physiological pH, those 2 OHs are deprotonated. So what I have is 2 O- and then a double bond between the phosphorus and the other oxygen. Now, you, my students, I'm sure should recognize that that is going to be a situation which those O- are going to be in resonance with each other. So in effect, all 3 of these oxygens become equivalent. In order to tell the computer we're going to do that, what we'll begin by doing is selecting this bond by clicking right in the center of it, and then right-clicking on it, and going Change Bond, and changing it then to partial double. We'll do that to all 3 of these bonds. So that we now have a nice, beautiful phosphate group. I now want to minimize the energy level of this new molecule, this analog of Tamiflu that I've created, by double-clicking on it to select it, and then going Modify, Drying Minimize. We'll now select 1,000 iterations, and we do want to include intermolecular forces by checking this box. We now click OK, and it begins to minimize. Now, once it's all finished, you might realize that you can't really see all 3 of those oxygen atoms clearly. If you click the rotation tool up here, though, and rotate around, you can see that they're all there, and they have hopefully been rotated around in some way that kind of places them, hopefully, kind of spaced out. To be quite honest, I don't really like that because I'd like to see more of a 120 degree or close to 109.5 degree bond angle between those. So what I'm going to do is I'm going to grab one of them and drag it over a little bit, and then I'll double click to select my entire molecule and then repeat the process of drying minimize. We'll now do it again and see what happens. Yeah, using my rotation tool and rotating around, that looks a little bit better. And this goes back to the thing I taught you guys about the fact that sometimes the software is just trying to find a local minimum energy level, which isn't necessarily the absolute most stable conformation you can get for this molecule. Now we'll go ahead and look at our enzyme again by going to View, Show All. If we click this black box, it will put everything there centered in our screen. I now want to double click my molecule right there to select it, and I'll now cut it out by selecting the cut tool and then paste it back in. That tells the software once again that that is a separate molecule from the rest of the enzyme. What I now want to do is calculate my delta E for the complex. I do that by going up here to Modify and selecting Drying Minimize. I'll do 0 iterations, and I'm sure now to check this box, Include Intermolecular Forces, because that will now calculate all of the intermolecular interactions between my modified Tamiflu and the enzyme itself. We now select OK. The minimization is now done. Let's go up here to Window and choose New Data Table. Go down and click on the Molecule tab, and you'll notice these final, what the flying... Okay, hang on. Now, I should warn you that for some reason that I'll never understand, occasionally the software will delete one of the oxygens that you placed on the central phosphorus atom on that part of the molecule that we modified. You should pay attention to that. If that happens, go back, remodify it, and then reattempt. Let's go ahead now and double-click on our molecule. We'll now select Cut, and then Paste to put it back in. This tells the software that this molecule is different from the rest of the enzyme active site. We now want to calculate delta E for the complex. So we'll go here to Modify and select Drying Minimize. We want to do 0 iterations and check all 3 boxes, including the intermolecular forces here includes all of the interactions, both positive and negative, between this molecule that we've made and the active site. Thus, the final combined energy levels that we calculate out of this should be the energy level for the enzyme substrate complex. We now select OK. The energy minimization is done. We now go up here to Window and select New Data Table. We go down and click the Molecule tab, and you'll see the final driving energy levels, 505.05 and 54.27 for the enzyme and the substrate independently. If we add these two numbers together, we get 559.32, which is the final energy level of the enzyme substrate complex. Now we need to get the energy levels independently of the enzyme and the substrate. So we'll go here to Window and go back to our molecule 2:1. Now we go ahead and select Modify, Driving Minimize, except that we deselect the Include Intermolecular Forces so that we can get the independent molecule and the enzyme separate from one another. Let's go ahead and click OK. Now go to Window, New Data Table, and select the Molecule tab. We now have new numbers, 527.83 and 54.27. If we add those two numbers together, we get 582.1. That is the sum total of the individual energy levels of the enzyme and the substrate independent from each other. To calculate the overall energy level for this reaction, as I outlined in our earlier video, we need to take the delta E of the enzyme substrate complex and subtract from it the energy levels of the enzyme and the substrate independently. So what we'll do now is take our enzyme substrate complex energy level, which was 559.32, and we subtract from it the combined sum of 527.83 and 54.27. That final number comes out to be negative 22.78 kcals per mole. That is, of course, a negative energy of reaction, which indicates that this is energetically favorable. It is not as negative as the original Tamiflu that we calculated in our earlier video, so this particular analog is not necessarily quite as favorable, at least by these initial calculations. I should warn you, of course, that because the software is always trying to find a local minimum, that your numbers might not be exactly the same if your molecule was for some reason tweaked a little bit differently from the way mine was on screen. Let's go here to Window and select Molecule 2.1 to go back to the window that we were just looking at. Your assignment for this lab is to continue modifying this Tamiflu molecule. You can, of course, click on it, go to View, Show Only, and then make it big, and then continue to change parts on it, much like you did in the previous lab. If you like, you can change those parts to match or correspond with some of the different modifications that were done in the paper that I just showed you. Then I want you to calculate an overall delta E for the new reaction for your new modified Tamiflu, which once again should have phosphate group out here at this position. I'd like you to make a table showing maybe 5 to 7 molecules that you've created with delta E levels for them, and then hand them in. The hope is that you can create a medicine that has a more negative delta E than the original Tamiflu, and therefore might be a more viable or more potent drug candidate to help combat this particular strain of flu. That is exactly what we might do, for instance, if this strain of flu became resistant to Tamiflu. And that's the reason why this lab is called The Flu Fights Back. Until next time, my wonderful students, I hope that you'll have an enjoyable rest of your day.